And we're back. Welcome back and happy Tuesday. Today, we will pivot our focus to clustering, so-called unsupervised learning, specifically k-means clustering. But before we begin, some administrative bits. And so there's a video on YouTube I'd like you to watch. Great description. A colleague with whom I attended graduate school. And also the reading. There's the coordinates for it. I've also put it on the course Blackboard. All right. So where we last left off, we talked about the learning algorithm. And we explained the learning algorithm as a search through a family of functions. We gave the example of the family of functions consisting of a linear model in two dimensions, namely a line on the plane. And in that, we have two parameters, m and b. And in the inset in the upper right-hand corner of the figure, we have a representation of the set of lines on the plane. We'll call that h subline. Now, of course, for any choice of b, the y-intercept, and the slope m, we define a different line. And so our search then traces some path from an initial line to another line to another line as we're searching by action of the learning algorithm through the space of hypotheses from our hypothesis set. And we said we can generalize this linear model in an arbitrary d dimensions. We call it a hyperplane. And so we went back to that credit approval problem. We have our input vector representing our customer records in d dimensions, and then we also have our d-dimensional linear model. We included a threshold, and that threshold is a score representing the weighted sum of each component of the linear model along with each component of the input vector. And so we have our score, and that score was the threshold that determines whether or not the current linear weights in weighted combination with the input vector attributes exceeds the score or does not exceed the score. And so we approve credit if the weighted sum exceeds the score. Otherwise, we deny credit. All right. So we then cleaned up this expression in closed form. We obtain a function that describes our working hypothesis, h of x. And so we took this cleaned up version, expressed it in vector form as the weighted sum or the sign of the inner product. Okay, and this was our h of x. We then, in a series of iterations, select misclassified input points and apply the so-called PLA update. W gets w plus yi xi, which has the effect of moving the decision boundary, i.e. selecting a new hypothesis for consideration based on an error measure. So let's take a look at an unsupervised learning application. Previously, in PLA, we have the class labels. We have the ground truth class labels, yi corresponding to an input vector, xi. Now, there are certain problems sometimes where you don't have labels. Now, of course, if you don't have labels and you want to learn something about your data, your historical data, the only thing you have are the values of the features. So the goal then, if you don't have labels, so-called unsupervised learning, is to identify similarities or patterns among the data points that you have. And so if you can identify similarities, you can certainly group them together and then go in after the fact and analyze and make statements about the groupings. So let's start with an application to drive this home, to motivate what unsupervised learning can do for you. So let's assume we have features that describe customer purchasing behavior. We go into super duper market, and it has one feature that describes along the horizontal axis the so-called post-consumer content, the recycled paper products. Now, of course, you can have some products like Kleenex on the left-hand side of the horizontal axis that have very small amounts of post-consumer content, ranging on through napkins, which can have a little bit more post-consumer content, on through paper towels, which can have a lot of post-consumer content. We also have another axis representing this vertical axis, representing the acidity in a beverage. So baby formula has very low or relatively low acidity. Milk has a little bit more acidity than baby formula, and Coca-Cola has a lot of acidity. And so for every customer purchase of a particular item or set of items, we can register each customer based on the things they buy. So this customer has bought Kleenex and baby formula. For example, this customer has bought paper towels and something that is closer to Coca-Cola. So what if we're interested in 3 total groups? So we want to take this set of data points representing all of the purchasing behavior for all of the customers, and we want to assemble them into 3 groups. So we propose 3 groups, G1, G2, and G3. So then, randomly, we start assigning points to groups. It's like flipping a 3-sided coin or rolling a 3-sided die. For each one of those points, you say, is it going to go in G1, G2, or G3? And you just make a random assignment. And you do that for each point in the data set. So this results in an initial grouping. Now, of course, that grouping might not be correct relative to the points that landed in each one of those groups, G1, G2, and G3. But that doesn't matter. We're going to fix this up over time. So each point has an XY coordinate or a horizontal and a vertical component and value in feature space. And so you might have a certain level of acidity and a certain level of post-consumer content for a particular data point in feature space. And so you start out with your groups that you've randomly assigned, and then for each group, you're going to add up the distances between every 2 pairs of points across every single group. So let's call L such a distance, and it goes from I, for the outer summation, goes from 1 to the number of data points in group 1. And so what you're doing then is you're saying, all right, well, let me take each one of those components, each one of those vectors, and take their difference along the X direction for the X feature and the Y feature, and we're going to add that up across all of the points in group 1. And so, of course, you're only going to do this for the upper triangle or the lower triangle representing the adjacency matrix. But nonetheless, you get a picture that looks like the following. These are all your data points that are in group 1, and L is just the sum of all of the pairwise weights between data points belonging to group 1, regardless of if they're more similar to one another or not. And so now what we enterprise to do is then take our measurement, L, pairwise between each group, all the data points, and we're going to search for some assignment of points to groups, other assignments that minimize the sum, L, for each one of these groups. So you might be rehoming, so some points are going to be shuffled to a different group because that might contribute a smaller value to that group's component of this summation. All right. So once you get the optimal groupings, it means that those assignments are the best assignments you can have. Then after that, you arrive upon a resulting grouping. Of course, you don't know ahead of time what to call those groups. So once you have your grouping, you then compute the center member of that group, and that center member is going to be the representative of all of the data points that are in each group. So the center is important. Then you go in and you perform an analysis of each group, and you would describe what you believe those groups should be called. And so going back to the super duper market example, if we have a group whose post-consumer paper content is low, like Kleenex, and the baby formula, the acidity is low, then we might call that the group of new parents. Or in the middle, the group that has a household with children. Or on the right, you have a house with teenagers as the group name that you give it. And so this post-analysis of the results of clustering, those natural groupings between data points, is really, really important. All right. So now, after you do this, let's imagine then a new customer comes into the shop. He or she buys some items, and let's say buys an item that has post-consumer content, as well as an item, it's a beverage, that has some level of acidity. So then you take that new customer and you locate where they are with respect to post-consumer content and where they are with respect to acidity, and that's going to be where this new member, this new shopper, is going to fit among all of the previous historical data that represents customers that arrived at the retail establishment. And so a new customer buys a napkin, you predict that it's a house with children. And now that you know it's a house with children, or it's closest to that grouping from the previous data, you can now go ahead and do something like offer couponing for milk or other items that people in that group typically buy. So if you've ever gone to a supermarket like Safeway or Acme and you buy some things and then a custom receipt gets printed out and you wonder how they did that because the thing that you bought had something to do with the coupon, well, that's unsupervised learning, specifically clustering in action. So there are some questions, though, with unsupervised learning. What is a good distance measure? Because how you measure similarity between points to see if they should be in the same cluster is based on the distance measure. And not all distance measures are the same. What is the best number of groupings, or how many clusters? Now, of course, if the cluster count is too high, you're going to get some very specific results. If the cluster count is too low, you're going to get too much generalization in your cluster results. So the question then is how many also axes are appropriate for the representation. So the best number of groupings talks about how specific you want to be and if the data can support it, but the number of axes talks about the appropriate representation, feature space representation. How much data is needed to accurately predict behavior? That's important. Can you afford to do it only on a little bit of data? Right? So this next point, scaling to large data sets, it matters. Will it work when things get really, really big? And how novel should predictions be? You may want to show them an item from a nearby group. Will it predict things that are more similar or less similar? All right, so let's take a look at our data. So we have our data set, and this data set is of size n. We have x1, x2, x3, up to and including x big N, and each of these data points is defined in d-dimensional feature space. And so for x1, we have x11, which is the first feature. We have x12, which is the second feature of the first input vector, up to and including x1d, which is the dth feature. And so for each xj, we have the first feature of the jth data point, up to and including the dth feature of the jth data point. So let's continue on. So let's take a look at the cluster centers. So we have some number of clusters, k many of them. You could call them groups of points, and this is what we desire. Now each cluster has a name, S1 for the first cluster, S2 for the second cluster, etc., up to and including S sub k, where S sub k is that kth group of data points. And so each cluster has a center. We're going to call this the cluster's center point, and we're going to calculate the cluster center point as the mean, specifically the sample mean, of all of the points within the cluster. And so we select some number k of randomly initialized cluster centers. Then we're going to assume each cluster center point, or mean, is as follows. So we have mu1, which is the center for cluster S1, mu2, which is the center for cluster S2, up to and including mu sub k, which is the center for cluster SK. Now, because these means are computed from the data points, each of these cluster center points, or means, is going to be defined also in d dimensions. And so for the first feature, that's constructed as the sample mean of the first feature of all the data points. Mu sub 2 is, or the second feature in our cluster center, is computed as the mean of the second feature for all the points in that cluster. And similarly, the dth feature for the cluster center is going to be computed from the sample mean of the dth feature of all of the data points in that cluster. And so we do that for all of the clusters, and each of the features of the cluster centers are the sample mean of the respective feature for each of the data points within that cluster. And so here, in general form, we have the ith cluster center, mu sub I, is mu sub I1 for the first feature, up to and including mu sub ID for the dth feature. And this is only for the points within the ith cluster. And so the ith cluster center is going to be the representative of the ith cluster. And so we have S sub I has a center, mu sub I, in d dimension. And then we also have our set of data points, xj. And those data points, xj, are distributed among all of the cluster that we have defined. Okay, so with that, we will end there. And as usual, please stay healthy, stay safe, and I will see you all on Thursday.